Hello, calculus. Been a while. Hope you're all having a fantastic day. Today is the day we're going to talk about implicit differentiation. Now, implicit differentiation is the same thing as differentiation. It's the same thing as taking the derivative. It's just now we're doing it implicitly. So what I'm actually going to do is have you go about midway down your notes here. It gives you an example of the difference between explicit and implicit. Now, explicit is when you have something defined as y equals something, right? What we say is that y is defined explicitly. All right, y is defined explicitly. That means that it's y equals something. Implicit, all right, this defines y as a function of x. Scoot this over here. As a function of x, but this is implying that. That's where we get the term implicit. It's implying that y is dependent on x. See, up here in this type of explicit equation, we have y is equal to, and if I change x, that's going to change y. So we would say that y is absolutely dependent on whatever value of x you get. Now for implicit, see how we have x's and y's jumbled up together here? We've got a couple of different variables next to each other. Y is not defined clearly as y equals something, so we can't call y dependent on x unless we say that it's implied. It's implicit that y is dependent on x. So really the only difference between explicit and implicit is that your x's and y's are jumbled up together. When we take derivatives, we take it the same way, but it's all going to depend upon how we actually say the derivative, or what we're actually taking the derivative with respect to. Now, you know how to say this with words. This is the derivative with respect to x. That means you're taking the derivative of your x's. And then you're taking the derivative of your y's here. You're taking the derivative of your v's here. So this is actually going to get into some pretty interesting stuff. First, the derivative with respect to x. If you were to take the derivative of x, this is d of dx of x. You're taking the derivative of x with respect to x. Well, the derivative of x is just 1, right? This is kind of like saying dx over dx. That's just 1. So if I wanted to take the derivative of y with respect to y, dy dx, then that's just going to be 1. Right? Same thing over here. The derivative of v with respect to v is just 1. The derivative of v is 1. But then we get into a couple of other things. We get into the derivative with respect to x, but what happens if I'm taking the derivative of y? Well, if that's the case, then the derivative of y is just dy dx. It's the derivative of y with respect to x. The derivative of v is dv dx. The derivative of t is dt dx, right? And you can fill in all of this just going off of that little bit of information. The derivative with respect to y here, the derivative of x with respect to y, the derivative of x with respect to v, the derivative of y with respect to v, the derivative of v with respect to y, derivative of t with respect to x, and the derivative of t with respect to v. Okay, so all you're doing is just taking the derivative. It's just when we're taking the derivative of y, we don't know what it is because we're taking it with respect to x right here. So we would say dy dx. It's the derivative of y, whatever that happens to be, right? So let's find some equations and some interesting things that are going to happen here. First off, x squared. Well, the derivative of x squared is going to be 2x, right? because you're taking it with respect to x. If I take the derivative of y with respect to x, my regular derivative rules still apply, so this is going to be 2y. But now I'm taking the derivative and these variables don't match. So what I'm going to do to compensate here is put a dy dx on the back end of it. So this is the derivative of y with respect to x. And then we have the derivative of v, which is going to be 2v dv dx. Right? And the derivative of t squared is going to be 2t dt dx. So we've got a couple of things going on here. We're taking derivatives with respect to x on this top line. So it's going to be different than what we've been doing in the past, but only in the way that we're adding on a dy dx, dv dx, dt dx. Okay? So from there you could go, say you want to take the derivative of x with respect to y. Same thing here, it'd be 2x, but now we need to throw on dx dy. We're taking the derivative with respect to y. And it's going to be the same all through here. And then with respect to t, we have 2x, which is this derivative, and that's dx dt. Notice we're taking the derivative with respect to t. You've got to look at this variable. You have to come back to this variable and they have to match. If they don't, you have to put this on here to compensate for it. And we can go through and we can fill in all the rest of these. I'm going to let you do that on your own. Just take your time. It's easy enough. It's easier said than done. Or it's easier done than said, rather. This shouldn't be that difficult of a concept for to fill in the rest of these. But just for this last one here, the derivative with respect to x, we've got, this will be 6x, right? Actually, no, let me do this here. With respect to y, this is 2y, and since the variables match, I don't need a dy dt, or a dy dy, because if I did write, let me do this really lightly, if I did do a dy dy, isn't that just 1 for dy over dy? So this would end up going away anyways. Same thing down here for the derivative with respect to t of t squared is just 2t, and then you'd have a dt over dt, which is just 1, so it would all go away. So here we have 6x, the derivative with respect to x of this equation here would be 6y dy dx, right? 6v dy dx, or excuse me, dv dx rather, and 6t dt dx. So there's going to be a couple of things that are going to be a little bit different, but again, all you're doing is these same methods. You're just compensating for that dt dx, dv dx, or dy dx. So I'm going to fill in this one here. The derivative with respect to y again is just 6y, because dy over dy would be 1. The derivative here would be 6v, because dv over dv would be 1. And you can fill in the rest there when you have the time. Okay, now going from here, the definition of implicit differentiation, here's what you're going to do. Differentiate both sides with respect to x, and this will result in a relationship between xy and dy dx. All right? So there's a couple of guidelines for these, but let's start off with just a basic one here. Y is equal to 2x squared. Now this is explicit. This is an explicit definition because it says y equals. So if I want to take the derivative, you take the derivative of both sides. Now you've actually been doing this already for quite some time. You just didn't know it as this. If I take the derivative of y, just like I did up here, the derivative of y with respect to x, isn't that just dy dx? Then take the derivative of this side, and that's just going to be 4x. Now technically there has always been this dy dx, or excuse me, dx dx lingering on the side here. this dx dx, but that's 1, so we've never worried about putting it there. Okay? Now when we do this implicitly, now we're changing it up and we have y squared. So I'm going to take the derivative of this side just like I did over here. The derivative of y was 1 dy dx. The derivative of y squared is going to be 2y dy dx. I have to compensate, so I have to put this dy dx on here, is equal to 2, and just for kicks and giggles, let's go ahead and put it on here, dx dx, just so you can see what happens to this. So dx dx goes away. Now the difference between this equation and this equation is that dy dx is the derivative. But over here we've got a dy dx, but I've got this 2y in front of it. And I need to get dy dx on its own because I'm trying to find the derivative. And the derivative is dy dx. So it's simple enough. What I'm going to do is divide by 2y. So dy dx is going to be, your 2's will cancel, and it's going to be 1 over y. That is the derivative with respect to x. So the only thing that changed here is that I had a y squared instead of just a y. The dy dx came from your regular derivatives. We've used this before for notation for a derivative. So we just have to take the derivative of the y squared, and there's our notation. So we have to compensate with a dy dx. And most of the time, we're going to deal with dy dx, at least for the start. Okay? So let's take a look at some of these guidelines here. This is guidelines for implicit differentiation. First, we're going to differentiate both sides, left and right. We're going to collect all of our dy dx's to one side, factor out dy dx, and solve. So basically, once you differentiate, solve for dy dx. And these two steps are kind of, second and third step is kind of implied with number 4. Okay? So let's try a couple of these and see what happens. Example number 3 says x squared minus xy plus y squared equals 7. Okay, so I need to take the derivative, right? Let's take the derivative of the left-hand side. So the derivative first, what's the derivative of x squared? Well, that's going to be 2x. Now I'm finding dy dx, so you know you have a dx dx right here, but it's 1, so it'll just go away. Bring down your minus sign. And then we've got a product rule right here. Ooh, a product rule. First d second plus second d first. So I'm going to do this. I'm going to open up a set of parentheses because this minus sign has to go to your product. So I'm going to open up a set of parentheses, and it's going to be first times the derivative of the second. Well, what's the derivative of y? It's 1 dy dx. I've got to compensate with this derivative. Plus the second y times the derivative of the first times 1. Okay? And then plus, I've got my y squared here, so I'm going to take the derivative of that. It's going to be 2y dy dx. Okay, so I take the derivative, which is 2y, and then I compensate with a dy dx. And then on the right-hand side, the derivative of 7 is 0. Yay! Okay? So, number 1, differentiate both sides. There's both sides differentiated. Step number 2, collect all dy dx's to one side. So let's go ahead and distribute this negative here, and let's drop these parentheses. 2x minus x dy dx. Let's see if I can change to a sharper pencil. Minus y times 1 is y plus 2y dy dx. And what I'm going to do is get all of my dy dx to one side and everything that doesn't have a dy dx to the other. So I'm going to take this minus 2x here, minus 2x I'm going to add y, and what that's going to do is leave me with just my dy dx values. So I'll have a negative x dy dx plus 2y dy dx equals negative 2x plus y. If you wanted to rewrite this as y minus 2x, you absolutely could. It's up to you. And then factor out dy dx. I'm trying to solve for dy dx. Big picture here, I am trying to solve for dy dx. So I'll factor out dy dx, right? And then to get dy dx by itself, simply divide over this part. So I end up with a negative 2x plus y, that comes from right here, over negative x plus 2y. And you have just completed one of your first implicit differentiations. Okay, so again, look at what I did. I took the derivative, compensated when I took the derivative of a y. Anywhere I took the derivative of a y, I'm going to compensate. Now, the reason why I'm compensating with just y is because I'm trying to find, down here, sorry, I'm trying to find dy dx. I want to actually solve for, just like I did here, I want to solve for the derivative. Right, so let's try a couple more here, two more. First, you have x squared y and 2y cubed, 3x plus 2y. So I'm going to differentiate both sides. Now, the problem with this one, I've got a product rule. So I'm going to set myself up a set of parentheses. And it's first x squared times the derivative of the second. So it's going to be, 1 dy dx, right, plus the second times the derivative of the first, times 2x. And then plus the derivative of 2y cubed is going to be 6y squared dy dx. I've got to compensate because this is not x. The derivative of 3x is 3. Plus the derivative of 2y is going to be 2 dy dx. So anywhere you have a y, you have to compensate your derivative with a dy dx. All right. There's nothing going on with the parentheses here, so we can go ahead and just drop those. And let's kind of get some things in order here. I'm going to have my x squared dy dx plus 2. I have a thing for putting things in alphabetical order. Let's call that 2xy. Got a big thing for putting stuff into alphabetical order. And then I've got plus 6y squared dy dx, 3 plus 2 dy dx. So all I did is drop my parentheses and put these in order, at least on that portion. From here, get all of your dy dx's to one side and everything that doesn't have a dy dx to the other. So it's going to be x squared dy dx is going to stay right where it's at. I'll have a plus 6y squared dy dx. So this one, and this one. Since I'm bringing this over, it's going to be a minus 2 dy dx. And that's going to be equal to 3 minus, and I'm going to take this 2xy, move it on over. So take your derivative, simplify it a little bit, get all of your dy dx's on one side, everything else to the other, factor out dy dx. I got x squared plus 6y squared minus 2. Last step, divide over x squared plus 6y squared minus 2. Divide it over. Dy dx is equal to 3 minus 2xy over x squared plus 6y squared minus 2. And there you have it. Divide this over, and you're set. So see, it's not really that much of something going on. Now, I will admit, once you get to your signs, or once you start using your chain rules, like on example number 5, the last one here, this can get a little hairy. So stay with me on this, okay? First, on the left-hand side, right here, we've got a chain rule, right? I've got sine and I've got a function inside of it. So let's set this thing up over here. I've got sine, and then my little candy inside is going to be x squared plus y. But when I do my derivative, I'm going to set it up the exact same way I would any other old time. The derivative of sine is cosine. Candy inside won't change. X squared plus y. Is that focused enough? It's a little better. And then the derivative of x squared here is 2x plus the derivative of y is dy dx. So you know that I have to multiply these two things together, right? I'm going to end up multiplying them together because you multiply these together. So the derivative of the left-hand side is going to be, let me see if I can write this out here, cosine of x squared plus y times 2x plus dy dx. All right, and I just use the brackets so I know I'm separating that from my cosine. It really doesn't make any difference. Okay, chain rule on the right-hand side again. So I've got the y squared. Oh no, sorry, this is a product rule. What am I talking about? This is a product rule. So we've got the first y squared times the derivative of the second, which is 3, plus the second, 3x plus 1, times the derivative of the first, which is 2y dy dx. I'm sorry this looks so jumbled up. Let me see if that'll separate it, if that'll help. First times the derivative of the second plus second times the derivative of the first, 2y dy dx. Okay, to make my life easier, what I'm going to do is distribute everything that I can. So I'm going to distribute this cosine x squared plus y into here and here. Okay, so what I'm going to end up with, this is going to be a little big at first, but what I'm going to end up with is 2x cosine of x squared plus y plus, then we've got cosine times dy dx. Now usually dy dx goes at the end, so I'm going to do cosine x squared plus y times dy dx. And that's going to be equal to, let's go ahead and simplify this thing out. We've got a 3y squared from this guy right here, 3 times y squared. Then we've got 3x times 2y dy dx. So 3 times 2, if you distribute this into here and here, 3 times 2 is 6xy dy dx. I want to make sure you see where that's coming from. 3 times 2 is 6. X times y times dy dx. X times y times dy dx. Plus, 1 times all this is just going to be 2y dy dx. A little bit bigger, but that's okay. We can cope. Because the next step is going to simplify this down. I'm going to get everything that has a dy dx to the left and everything that doesn't have a dy dx to the right. Now, it doesn't matter left or right. I just picked left because I like left. So I'm going to get all my dy dx's to the left. So this guy is going to stay and these two are going to come over. So I'm going to say it's going to be cosine x squared plus y dy dx minus 6xy dy dx minus 2y dy dx is equal to, and then this guy and 3y squared are going to be over here, so it's going to be 3y squared, that stays where it's at, minus 2x cosine x squared plus y. I'm 2 steps away from being finished. All I have to do is factor out my dy dx and solve. Factor out dy dx and solve. So I'm going to have dy dx is equal to, oh wow, not is equal to, excuse me. Dy dx times, if I factor it out, cosine of x squared plus y minus 6xy minus 2y. Factored my dy dx out of all those terms, here, here, and here, is equal to 3y squared minus 2x cosine x squared plus y. My last step, and I'm done. Dy dx is equal to all of this divided by all of this. 3y squared minus 2x cosine x squared plus y all over cosine x squared plus y minus 6xy and 2y. Okay, for the last couple of minutes here, I just want to tell you something. Be kind of candid with you for a moment. I struggled for so long with implicit differentiation when I was in high school, even somewhat into the college years, because I couldn't, my mind couldn't be wrapped around how easy it was, and so I struggled with it. As long as you can remember that you're taking the derivative of what you see, and if it happens to be a y, tack on a dy dx. Whatever you're taking the derivative of with respect to. We'll get into later where we did like on the front, the dv's and dt's, the derivative with respect to time, with respect to v. All that's doing is changing the variable. The principle is the same. Okay? So when we get into this, I want to make sure and take this nice and slow. Make sure that you go back and rewatch if you need to, and then we'll go from here. I really want your confidence to be built up in this, okay? So implicit differentiation, it's an awesome thing. Have a great one.